Break is our ongoing forum in which we discuss new and evolving technology, all in about the amount of time it takes to drink a cup of coffee. I'm your host, Eric Glatfelter. Joining me in the studio today is Aaliyah Fahout. Aaliyah, welcome back.
Thanks, Eric. Hi, everyone. Welcome to Season 11 of Coffee Break. We are live every 2 weeks and ending with our Cocoa Break in December. We are currently live on YouTube, Facebook, and LinkedIn, and you can participate in today's episode by leaving your questions and comments in the chats, or you can email us at livestream@microchip.com after the broadcast. Don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Eric.
All right, thanks, Aaliyah. Our topic today is enabling an omnidirectional grid for a more sustainable future with silicon carbide. Joining us remotely is Dr. Kevin Spear. Kevin, I checked the logs and you were last with us in April of 2022 to talk about our latest portfolio of 3.3 kilovolt silicon carbide products. But today we're talking about a broader application area. We talk about efficiency a lot in the semiconductor world and the electronics world. Often it is at the point of consumption or about things that we use personally, like our computer or our favorite device or our TV. Today we're going to talk about the grid, and the grid is kind of an abstract term and kind of a specific term at the same time. So can you walk us through a little bit about the different points in the grid and what that means?
Yeah. Thanks for having me back, Eric. Apparently, the first time I didn't embarrass anybody. So
No.
thanks for having me back.
Not at all.
You're right. The grid is a very ambiguous term, and it becomes more ambiguous with the introduction of new concepts such as the microgrid. But maybe the best way to think about this is to think about the energy life cycle. If we consider that energy isn't just available for us to consume immediately, we have to remember that we must either harvest it or generate it. So that could mean a variety of different things. It could mean the mining of coal, the burning of fossil fuels to generate electricity, or it could mean the harvest of wind energy or solar energy. So that is all on the opposite end of the spectrum of what we call the grid from the point of consumption. We have this entire infrastructure between those points of generation and consumption that I feel like when we talk about wide bandgap semiconductors and increasing efficiency, we all too often ignore the rest of the energy life cycle. We focus instead too much on consumption. But when we talk about the grid in today's topic, we're really talking about everything between the points of generation and harvest and consumption.
Okay, so why is it so important that the grid itself and all those different points be efficient? What kind of numbers are we talking about?
So the fact from the International Energy Agency that when I've been preparing for these presentations and these talks, that really woke me up is of all of the energy we harvest and we generate, of all that energy that's available to us, more than 2/3 of it gets lost. So our current grid is terribly inefficient. And then one of the big trends where that ties consumption and the grid together is the massive uptick in adoption of electric vehicles. Now, it's true that electric vehicles will save greenhouse gas emissions in a major way, but we're going to have to charge these electric vehicles as well. So to put that into context, in 2021, the United States had a total electricity usage of about 4,000 terawatt hours. The International Energy Agency predicts that by 2050, due to this huge uptake in electric vehicles, we're going to need 2,000 terawatt hours just to charge those electrified vehicles. So the question then becomes, how are we going to come up with all this additional energy?
Sure. Now, a couple things before we move on. So just the scale of the energy here is kind of mind-boggling. So when we talk about the efficiency of this laptop or a phone, we talk about making it more efficient, so we're squeezing every last milliwatt out of the efficiency. Now you're dropping numbers that are terawatts, right? So even the midpoint of that, charging an electric vehicle is kilowatts, right? So we're talking about we're talking about orders of magnitude more than the energy used for a personal electronics device or something in the home.
Yes, that's right. So laptops, your smartphone, the power levels we're talking about here are in fact milliwatts.
Yeah.
Here, when we're talking about even electric vehicle, the traction inverter inside electric vehicles is typically rated at around 200 kilowatts.
Okay.
Now we're talking about charging the battery packs on thousands, potentially millions of these electric vehicles. So now we're talking about a grid that needs to be supplying powers at the levels of megawatts and even terawatts.
Okay. I guess the other thing I wanted to ask about and just clarify about the grid is we have all those losses, and each point in the chain, the energy life cycle as you called it, we have losses at each point, and many times, multiple times during that. So you may convert to a different voltage level, you've got losses in that conversion, then you transmit it, you've got losses in that transmission. Then it gets to a point you might convert it again, you've got more losses and transmit it again. Am I catching the gist of of all these different loss points?
It's like a waterfall effect, really.
Okay.
Every place where you convert the power from DC to AC, from one DC voltage level to another DC voltage level, every time you convert power, that is an opportunity for losses.
Okay.
And one other point that I'll add to that is the more we convert power closer to the point of load, the point of consumption, the lower the voltage those converters are, and the lossier those converters are. So the more that we can do this power conversion at a higher voltage level, the better off we will all be in terms of efficiency and actually being able to use more of the power that we harvest or generate.
Okay. Thanks, Kevin. Okay, so we want to talk about a more sustainable grid and an omnidirectional grid, which brings us to the topic of distributed energy resources. Can you explain that a little bit, and what are some of the challenges in using DERs in the grid?
Right. Distributed energy resources have long been sought after, and distributed energy resources. Let's think about the opposite. The opposite of distributed is centralized. Um, in times past and even today, we use predominantly centralized energy sources like coal-fired power plants, nuclear reactors. All of this power is generated in one central location and at massive, massive scale, and then the power must be ported hundreds, thousands of kilometers. And then back to your point, Eric, it's converted, conditioned, and all of these are opportunities for losses. These challenges create opportunity to go, instead of centralized energy resources, to distributed energy resources. So now we're talking about creating small localized grids that can self-sustain based on renewable energy resources such as a solar farm, a wind turbine, and then also it will have its own energy storage platform so that it can slough off the surplus energy that it's generating and harvesting but not being used. So this is what we mean when we talk about distributed energy resources. The challenge with incorporating DERs really rests with our current grid. Our existing grid is unidirectional. It has these passive transformers that are very large, very bulky, and frankly antiquated. The problem when we're trying to incorporate these DERs onto today's grid is that the DERs have different voltages, different frequencies, and all of that needs to be conditioned and tied into the grid in an intelligent way. Today's grid just can't do that.
Okay, so just to reiterate then, the different sources, the different distributed sources are going to have different power characteristics. And if we're going to put those onto a common transmission system, for example, they need to be normalized. So that's yet another conversion of the characteristics at different voltage level, power factor, or harmonics, or things like that?
Right. So, and this brings us into what silicon carbide can do to help, because
Sure.
we painted the picture of the opportunities and the challenges. Um, but what we can do is, instead of having a unidirectional grid that has these big, heavy one-way transformers, we can instead use solid-state transformers to actually condition, control, port the hour more efficiently. And now we don't have the difficulties of incorporating DERs. Um, Another point is, if we develop these solid state transformers with silicon carbide power devices, because silicon carbide can go to much higher voltage ratings, we can actually insert these SSTs directly into the grid. And that saves us the power losses, as we talked about before, of the low voltage power conversion.
Okay. All right. So we're skipping the worst, the least efficient conversion point at the lower power ranges. Interesting. Okay.
Right, right.
So can we take a look at a specific example? We've been talking a lot. We talked about EVs, for example. Can we take a closer look at how maybe silicon carbide can enable a more efficient EV solution?
Yeah, for sure. So there is an example that I love to refer to when talking about this topic, because it ties in the need for an omnidirectional grid in with the example of the problem statement we used before, which is EV charging and the additional demand that will place on the grid. So here's an example of researchers from NC State University and Power America, and they developed an EV charger that actually ties right into high voltage grid. And what they're able to do with the EV charger technology is disruptive. So point number one, they're able to reduce the size of a conventional EV charger by a factor of 9x. They're able to reduce the size by a factor, or I'm sorry, the size by a factor of 9x and the weight by a factor of 4x. And the efficiency improvement, again, compared to today's standard fast chargers, the efficiency improvement of tying an EV charger directly into the grid is improved by more than 60%. So again, coming back to the point you made earlier, Eric, about the scale of power we're talking about, 60% improvement in efficiency for milliwatts in a smartphone is not such a big deal. 60% gain in efficiency when we're talking about a multi-station EV charging network, we're talking about tens, hundreds of kilowatts of savings when we're talking about this efficiency improvement of over 60%. So more efficient, more compact, and less expensive to make, all by using high voltage silicon carbide to tie these end use cases directly into the grid.
Okay. So that's something that, in this case, would actually have an impact on, a normal consumer who's using an EV. If you go into a physical area that has charging stations, there's going to be more stations available. You'll be able to charge for lower cost, perhaps even faster, things like that. So definitely an impact on that infrastructure. Very interesting. Okay. Okay. So with silicon carbide devices, there are multiple suppliers in the market. What does Microchip offer in the space of silicon carbide?
Yeah, so for the silicon carbide business unit at Microchip, we have 4 product categories. So it all starts with the silicon carbide MOSFET and diode die, which we design and manufacture in-house. So that's the first product category. We do sell those bare die to customers. We then take those bare die and put them into either discrete package, which is through hole, mount, transfer molded type discrete packages, or we put them into power modules. Power modules, again, the power modules are something that we design and manufacture in-house. And then the fourth product category is gate drivers. These are no ordinary gate drivers. They're digital. They allow the customer to actually tweak the turn on and turn off speed of their power stage in real time using a mouse and a keyboard. You actually can design your system performance from your computer with these gate drivers, as opposed to using a soldering iron and a bucket of gate resistors. So these are the 4 product categories that Microchip offers in our silicon carbide business.
Okay, Kevin, thanks for that visual of the soldering iron, a bucket of resistors. You've taken me back many years to my days as a summer intern in the lab. But that digital gate driver would make the system development or the design easier for an end customer. They can optimize more quickly. Is that right?
Oh yes. One of the obstacles to adopting silicon carbide is it's one of its benefits. It's fast switching speed. Its fast switching speed leads to much higher efficiency, lower switch losses, but those higher switching speeds create transient overshoot oscillations, and these gate drivers save the designer a lot of time in optimizing the performance of those conditions.
Okay, great. So if somebody wanted to learn more about these portfolios, where would they start?
Well, we have a website, www.microchip.com/SIC.
Okay, very good. Kevin, thank you so much for sharing your expertise
Of course.
on this topic and joining us today. At this point, let's transition over to Aaliyah and see if we have any see if we have any questions from our viewers today.
Yes, Eric, we do have a few questions. This one is via LinkedIn, and it is, how does the efficiency of a SST compare to a traditional transformer, and are there any other advantages of the SST?
Yeah, so the performance of conventional transformers varies widely by the power range. I think at one end of the spectrum, we can talk about transformers being 60% efficient. At another end of the spectrum, we can talk about them being into the 90s. This is one benefit of SSTs, is that the efficiency will always be at a higher level. And arguably, the higher the voltage go in devices, the efficient they can be, depending on topologies. So efficiency at the system level is a very, very big advantage for solid-state transformers compared to conventional transformers. The other benefits are, with today's, passive transformers, we don't have a way to turn them on and off. There's no control. With a solid-state transformer, all of the devices that are in there doing the power management, processing, and conditioning are controllable devices. So it's just the intelligence. And coming back to the point of the omnidirectional grid, if we have solid-state solutions at every conditioning and at every conditioning and processing node, that gives us enormous flexibility toward what we like to call the omnidirectional grid. This is taking the exact amount of power, delivering it when and where it's needed. Should there be surplus, it's seamlessly shuffled off to an energy storage system for later use. So solid-state transformers give us all of that flexibility along with efficiency.
What a great answer, Kevin. Thank you. Another question we have is from LinkedIn, and it is, could you use this direct connected charger technology for grid-connected energy storage systems?
Yes, in fact, you can. This is an emerging space that I really attribute to high voltage silicon carbide. Now, it's true that high voltage silicon has been out here for a while, but it has its own performance roadblocks. Silicon carbide doesn't have those, so now we're opening up new application spaces, and we like to refer to these application spaces as grid-tied inverters or grid-tied converters. Just like the EV charger can be tied directly to grid, you can do the same thing with many other use cases, including, in particular, the example you used of energy storage system.
Great, thank you. Another LinkedIn question for you is, what are your thoughts on centralized DC supply of vehicle chargers versus rectification at each charging station?
So I don't have a very strong opinion on that. We leave those opinions to our customers. But what I can say is we see competing technologies in both directions. Um, I believe that as a macro trend, we see everything from EV charging and also data center, um, and even DERs. Coming back to the discussion about microgrids, everything seems to be becoming decentralized, as a general trend.
Awesome. Here's another question for you is what is the commercial status of high voltage SiC devices?
Yeah, good question. So at the 3.3 kV class, there are a few suppliers that are out there today. Microchip announced our 3.3 kV MOSFETs and diodes about 2 years ago now. So this is a good sign, I believe, for end users of these high voltage devices, because if you just have one supplier out there, it makes things difficult for high volume customers to adopt in the case of supply uncertainty, for example. So at Microchip, we believe the more the merrier, but we are taking a leadership position at high voltage.
Great, thank you. I think we have time for a few more questions. Here's another one. What are the roadblocks to HV SiC devices?
Yeah, there are. I would say there are a couple. Um, the first is the thick epitaxy needed to block these high voltages, and the second is high voltage power packaging. Um, these are two areas where I think the community needs some exploration, and particularly in the form of taking development to product level. For thick epi, um, there are two roadblocks. The first is the thicker you grow silicon carbide epitaxy, the more likely there is to be crystal defects that will degrade or ultimately kill the device. The second is silicon carbide is a very, very hard substance. And when you grow silicon carbide epitaxy on a wafer, you don't just grow it on the wafer, you grow it all over the chamber. So the first problem is getting the epi thick enough without defect content so you can make devices with good yield. And the second is the maintenance required to continuously produce these thick epi wafers at high volume. So that's the epi. On the packaging side, um, again, silicon has not pushed us to the extremes that silicon carbide has and will. So until today, we have been putting high voltage silicon carbide in packages that were made for high voltage silicon. And we are still doing that to a large extent, but what needs to be is we need to start designing high voltage, discrete, and module packaging for silicon carbide at these voltage classes.
Great, thanks, Kevin. I have another question for you, and I think this will be the last question. Why do we need to look at the power flow stages before the end user consumption stage?
The question, why do we need to look at the power flow stages before the end consumption?
Mm-hmm.
Yeah. So I'm not suggesting that we should do one before or after the other. It's that's not the point at all. The point is, I feel like we have been ignoring the rest of the energy life cycle for too long. I started off in silicon carbide in the late 1990s, and all of this time we have been promising carbide can do all of these high voltage processing. Something that I like to say is silicon carbide can do more than turn the tires on a battery powered car. So it's not that we should do one before the other. I'm calling on the community to consider the rest of the energy ecosystem. Um, to give a bit of data, however, so we talked about of all the energy we generate and harvest, 2/3 of that is lost, if just by the grid. If we look at just the transmission and distribution stages alone, those stages lose 5%. So that 5% of the energy that we lose in the transmission and distribution stages is power 1.5 American homes for an entire year. So again, it's not that we should look at one before the other. I'm just calling on us all to look at them all.
Great. Well, thank you, Kevin. You have been very insightful. Those are all the questions I have for you today. And audience, if you have additional questions or comments, please email us at livestream@microchip.com after the broadcast. And back to you, Eric.
All right, thanks, Leah. Thank you, Kevin, again for sharing your expertise here. Aaliyah, thanks for your moderating and introducing and the questions and bringing us to a close. And thank you to our viewers for taking some time out of your day. Please visit us at microchip.com/coffeebreak. There you can see the remaining episodes posted for the remainder of the year up until mid-December. You can sign up for notifications and you can peruse our library of previously recorded sessions. Again, thank you very much. See you next time.